Okay, so not so many today. Huh? No one comes forward. Why is it so far? Now I come close. Here. But you're striking today with both of them. Okay, let's quickly admit teams to come into class. Let's see. Put this over here. So before we start, Moses, would you mind praying for us, please? Okay, thank you, Moses. Moses, pray for us, please. Get something from the fact that you learn and understand. Amen. Thank you so much, Moses. So today's lesson, as we have communicated on the group, will be slightly different because we want to have that continuation for us to, sorry, excuse me, for us to sort of like make sure that we can cover good ground. Yeah? Are we together? So guys, online, I would like you to please, it's not easy to follow from that side. It needs a lot of discipline. So I can see most of us are there, and that's exactly what we wanted to create so that we have that comfortability. Nisuku, I see you are on. Welcome. How are you?
I'm good. How are you, sir?
Good to hear from you again, okay? So if it's possible, could you all please unmute yourselves so that you are in a place where it's really quiet, that you're focusing on the class. If you get background noise, we will mute you from this side. But again, guys, I know it's very difficult to be fully focused online, but it requires a lot of discipline. But I trust that we can do that. Okay, so first of all, we want to have an approach for today's lesson on question papers, right? We have given hard copies to the learners that are here in front of us. They've got some questions there. So before we do the lesson, like I said, the focus will be mainly on the questions. So I want to quickly show you something over there. I'm sorry, my YouTube has to be closed over there, so we don't get that background noise over there. All right. So what I want you to focus on is, like, we gave a copy of this to the learners here in class. I'm going to share that on the group as well. Again, we're not going to go through this in detail. It is just to give you an overview. Let's see if we can make it a bit bigger. It's just to give you an overview of this topic that we're going to be doing on electricity and magnetism. And if we scroll down with it, we can see it's quite a big topic. Like the first subtopic is on electrostatics. Now, under electrostatics here, we can see that this is where we'll talk about the static electricity and so on. So, all the different subtopics. Okay, sorry guys, let me just zoom that in. All the different subtopics, please go through that. We will try to cover as much as we can today. I hope we might be able to at least finish it. Sorry, I'm using two fingers here and this thing is not zooming properly. Okay, so current, what is the difference of voltage, your resistance, the relationship between those three concepts on current and your voltage and your resistance. And then we're going to look at electric circuits, and that's where the main part is, right? Electric circuits will deal with how do you calculate this different voltage or resistance and so on. And then electricity in a home, then is more on practical application, okay? And then we start with the simple magnetism, and then we want to see how the magnetic field affects electricity for different applications. Some examples would be the direct current motor, some principles to induce current through your electric and your magnetic fields, alternating current, and then finally on transformations. Okay. Now, what I want you to notice here is that if you go through the syllabus, you'll find places like this that have got some sort of formulas. Okay. Now, we try to summarize these formulas for you, right? Okay, on one sheet. Those of you that are here, it's on the last page. I think it's on the paper 2. So all the possible formulas that you will be using under electricity are summarized there. If I scroll a little bit up here, maybe let me see if I can find maybe another that show a formula. Yes, Mauritius?
Can sir please give an extra to Luther so he brings for me?
Is Luther here? Luther is not here. Maybe he's not coming. Okay, if he's here, I will give an extra one to him. Like again, look at this part here. There's a formula over there. There's another formula over here. So this is just to show you in the text as well what it is that you need to focus on. Again, if you go up a little bit, this shows now resistance in your parallel setting or your circuit in parallel. Another one here in series. So the reason why I'm giving you the syllabus is to see this. My advice to you is actually to highlight those points. For example, let's take a highlighter. You just highlight the points that you have. Or the, what do you call this? Okay, this one doesn't want to work there. I don't know why, but it's fine. I think you understand what I'm trying to say. Okay, so that's the first part. Okay, the second part of this would be now to look at the questions. Now, under the questions, we try to sort of like look at questions or possible questions that will be asked in the paper 2, how those questions are structured, and we try to cover as much as possible, and these are from past papers. Okay, we will still, before your exams, give you some additional questions. So we mix between the Cambridge and the Namibian papers. I think these are mainly from the Namibian papers. Now, what I want to show you here is that at the end of this, let me see, maybe I can put a view to have 2 pages next to each other, so the scrolling can be a little bit easier. Okay, so at the end of this, let's go through this. Like here, you can see they're asking a question on transformation. There's an electric circuit on the other side. Here, you've got a transformer, you see. So we try to see if we can cover as much as possible. Like here is transformers, here is static electricity. Okay, what happens to those different things as we go through that? Okay, right, I get some background noise there, thank you. Okay, so that's the idea behind this, but I wanted to take your attention to the last part, right? This is the electricity in a home, you know, the appliances. There you've got now your alternating current, the practical application of that, and then this question being repeated. Okay, this looks similar. And then at the end of this, okay, before I get to the end part, we've got some sample questions again on paper 3. So these are paper 3 type of questions, okay? The learners online, can you see this, or should I zoom this in a little bit more? Are you able to see that? Is that big enough?
Yes, sir. Yes, sir.
Okay, good. So again, the idea here is just to make sure that you understand when you're having a paper 3 and then you are looking at questions, this is now the one that we would say your alternative to practical paper. So I just abbreviated as ATP there. Now, under the alternative to practical paper, the approach is a little bit different, right? You've got the information in that first part and you need to extract the information and then you need to apply. Normally, in this type of settings or this type of questions, they would ask you to either draw a graph or to analyze a graph and those type of things. So again, a lot of learners are struggling with this type of questions. I personally feel that the paper 3 is a little bit more easier because most of the information is shared on the paper. So we're going to go through these questions as well on the paper 3. And then at the end, this is what I was talking about. This is where we've got most of the formulas. I can say maybe 99% of that is covered here. Sort of like a summary. So from 1, I think this one's go up to 20. I'm not too sure. So you would see maybe under transformations, what do you use for circuits? What's the formula for voltage? What does the Ohm's law state? What does that relationship entail? How do you calculate current? Or if you have, say, charge and time, you can calculate current like that. Are you following me? So those are the type of things we look at. So when we are approaching the questions, you can use this sort of like a cheat sheet type of thing, and then we answer based on this. Now, as I said, this has been given to the guys that are here in person, face to face. For you that is online, you'd see most of the questions on the screen. I'll put it on the WhatsApp group as well. You can print it out for yourself, or if you're in Windhoek, you can let us know. We can print it for you. You can pick it up. Okay. But yeah, those are some of the advantages we have when we are here in person. Okay. Right. So that was just to establish this background, just to approach. Now, I do not want to go through teaching. What I want to focus on for today is just sort of like a crash course, more or less like a revision type of thing. Okay. So under this, I'm going to go through this really fast, just to emphasize a few points as per the syllabus. Okay, and this is also recorded. We're going to share that YouTube link. It's good if you get on YouTube link, please go there, you subscribe, you like our page, so that we know we can also get, what do they call it? Become an influencer or something. What do you guys call it this thing? Okay, but anyhow, it's also just to create awareness of what we are doing for our Namibian people. All right. So, guys, as I said, I do not want to really go into teaching. This is going to be just a revision. Are we together? Remember, we said for electricity, we first start with static electricity. Now, the word static means station. It's not moving. So we wanted to know, but how does that happen if the charge cannot flow? You understand? So static electricity is, whenever you have touched someone, then you feel that electric discharge. You know that, right? Maybe you have been walking on a carpet and then you touch the doorknob or something, then you feel that electric discharge. Are you following? That is what we mean with static electricity. Now, under this, I'm just going to show you some few pictures just to strengthen the point here, okay? So the static electricity, by definition, is actually the imbalance of your positives and negatives. Where do the positives and negatives come from? Remember, we are dealing with what? We're dealing with atoms, right? So any atom has an electron, a neutron, and a proton. Are we together? So those electrons, neutrons, and protons that we are talking about are the ones that are going to be the positive and the negative that we have to deal with. Are we following? So the imbalance, that's how you create the charge. The imbalance of that will then create the charge. Then the movement of your electrons. Like here, static electricity is mainly known by if you have to rub by friction, right? You can move the electrons by friction. I just want to take a darker, maybe green would work there. Just the darker one so that we can see. I want you to notice here, we've got a cloth here and we have polythene here. Polythene is a type of plastic, right? So of course, because all of these are made up by your protons, electrons, and neutrons, you see your positive and you see your negative charges. Now, if you try to count the positives and negatives here, you'll see that they're the same amount, right? Like we could have 1, 2, 3, 4, 5 positives. Are we following, guys? And the negatives, is it 5? 4, sorry. And then 1, 2, 3, 4 negatives. The same applies for the clock. You have 1, 2, 3, 4, 5, and you also have got 5 positive charges. So what does that mean? They can cancel each other out and it will be neutral overall, right? So when you then rub the cloth against this polythene, then what will happen here? There will be a movement of your electrons, either from the polythene to the cloth or from the cloth to the polythene, all together. But in this case, we can clearly see that there are only 2 electrons left here. So the other 3 negative charges have moved to the polythene. What does that do? It does the following, that the positives now on the cloth are more than the negatives, so therefore the cloth would be positively charged because it's dominating or it's abundant. Are we together? And then on the polythene, the negatives will be more, therefore that would be negatively charged. Are you following? Is that making sense? So that is just to create that concept over there that you have. Just hold on a little bit. Maybe you could try with this end and see which one comes out better. All right. Sorry. Just quickly asking Mr. Simba for something. And then again, it depends on what you're using. So if you're using the cloth with acetate, okay, also type of material, then the movement of the electrons would now be from here to the cloth. You understand? What does that mean? That the acetate would now be positively charged because that is in abundance, and the cloth would now be negatively charged. So the movement can be from either side. Are you following that? Is that making sense? So this is now in a nutshell what static electricity is, okay? All right, this part that I have over here just explains everything that I've said in words. Yeah? So you can also take a look at this later. And then another example is again showing, just to strengthen the point here, how the charges are moving. We know that like charges here will repel, whereas unlike charges here will then attract. Are you following? So those are the different things that we look at. And again, just an example here that, you know, this is where the electrons are now moving from your hand up to the doorknob. You feel a bit of a electric discharge, which we could also say, yes.
You make the page bigger, please.
I think it's as big as I can. It's big enough. So I don't know. Let me just try to see. Does anyone else have the same problem?
Yes, sir.
Yes.
Yes.
Okay, let me just make sure that I am sharing the correct screen. Just give me time. Which screen am I sharing? I'm supposed to be sharing that screen. And that should be big enough now. Okay, so let's share that screen. Is that okay?
Yes, sir.
Okay, thank you for that. Okay, sorry, Swain, I did not see your chat box. Sorry, I was sharing the presenter's view over there. All right, so again, here, what we have here is to show that concept here, where it's used mostly is in the lightning. It comes a lot in your questions. What happens in lightning here? What happens is that you've got the clouds. Lightning only happens when there's a thunderstorm. So what happens with the clouds here? Let's get a darker color. What's going to happen here with the clouds? They rub against each other now. Maybe a lighter color on a dark background would be fine. They rub against each other, and because of that rubbing from the wind, there's friction, right? So what happens there is now a build-up of your electrons, and they are all the same charge. What happens to the same charges? They repel. So that repulsion is that discharge that we're seeing on the lightning part. Are you following that? Okay, so they would normally ask you in the question to explain that phenomenon about lightning. So you can put that in your own words, okay? So what does it show? It just shows the concept of static electricity. Are we following that? Are we all together? All right, so my guys there on the online, are we okay?
Yes, sir.
Yes, sir.
Right. You should make sure that you look nice at some stage. We'd also like to see you to make sure that you're in a conducive environment, that you're not in bed or whatsoever, that you can also see us. What is the problem?
No, sir. It's fine.
Is it fine? No. Now I want to see you, okay? So let us see, following what we are doing here on it. We will show you where we are so that our people here can also smile and see you. Okay? Can you see us?
So my camera is open.
Can you see us? Hello. They might not be able to see us, but let's see if we could go back to our situation. Okay, let's get that back. Then I think they are now hiding. They don't want us to see them yet. Okay, guys. Hello. Can you hear us?
Yes, sir. Oh, we got you.
Yes, sir.
You able to
So
see
we
how
can't see you.
you didn't see how senior citizens are here.
No, we can't see you.
Okay. Okay, I think we have to share the camera link, but we'll do it at a later stage there. We'll give you time so that you can put your, get on fleek, or what do you say? Yeah? But anyway, I was trying just to the concept of static electricity. So from here, we will then move over to the electric charge. Now, this is the electricity that is mobile, that can move. Are we following that? So this is now what we refer to as the electric charges. Oh, no, before we get there, that's actually the current. This is just to explain some few things on electric charges. Now, again, I want to just let you go through this again, but just to emphasize a point here, is an electric field is caused by the imbalance, right, between them. So you would see that between this picture over here and then this picture over here is just to show you the movement of that charge. How does it work from which side on the electric field? Again, this is just for enrichment, but what I want to get to is the electric current, your potential difference, your resistance, okay? Now your electric current and your potential difference, which we can also refer to as your voltage. I don't know whether you can see that color. It looks a bit too bright there. So let's do it like that. That's better, isn't it? So this is now your voltage, which means that there is a difference, a potential difference between the two. And then we have what we refer to as resistance. Okay, let's try. The blue will also not work, maybe the red. All right, so the resistance here. So basically, we want to look into current, which we abbreviate with the capital letter R, your resistance with the capital letter R, and then your potential difference known as your voltage with that. Are we together? The reason we don't use the C to represent current is because the capital letter C is used for the unit of charge, which is known as coulombs. Perfect. Okay. So again, let's quickly run through this. The next part is to show you the relationship between this. Okay. So we can use this to start off with a charge. Now the charge is denoted by the letter Q over here, right? You can get that by getting the product of your current and your time. So how much current has moved through that specific point in that given amount of time? Are we following that? So this is what we have on this side when we want to find the charge. So some ways that I remember this is to say cute it, nah? This is cute. So I don't know, you can find a way of remembering it. What I want to emphasize are the units that you're using. Are we following? So please understand the units that we're using. The time has to be in seconds. Your current is in amperes here or amps, and this is in seconds. And then, of course, you can say amps on seconds, right? But the common unit we use here is coulombs. Are we following? So the next part, again, just shows you some of the electric symbols that we use for an ammeter. This is a device. What type of device do we use there to measure what? To measure the current. Perfect. Those are the type of things that we'll be looking at. So I'll just quickly go through this. The ammeter, then how does it work? We can have it connected to the circuit. It needs to be connected in a specific way, right? So the ammeter can be connected to the circuit in series. What does that mean? In series means in the same line. Are we together? So as the charge is flowing here, it's in the same line. Are we together? All right, so this shows you how you can connect an ammeter. This emphasizes the connection of an ammeter. Okay, again, the next part now is just to show you a work example of calculating your charge. You need your current, you need to multiply that with time, and time has to be in seconds. Here we were given 5 minutes, right? So we would converting those 5 minutes to seconds. That's why we multiply it by 60, which becomes 300. Multiply this, this will be now the charge. It means that is moving at that specific time, at that specific point. Are you following, guys? So this is just to emphasize what I was supposed to work out over there. The next part is for you to understand the difference between a direct current and an alternating current. Are we together? Direct current. I taught yesterday, what was the topic we were doing in chemistry? Electrolysis, right? Or electrochemistry. So that whole thing about your anode and your cathodes and what, when you have the basic electrolytic cell, you can only use direct current. Are you following me? So this is now when you are starting at one point and maybe from this point, you're moving to that point. Alternating current can move back and forth, back and forth. Are we following that? All right, please know the difference between these two things. Another one would be the conventional current and then the electron, the flow of your electrons. Sometimes we refer to that as the electron flow. Look at this, right? Conventional belief that you're flowing from the positive all around the circuit, you light up whatever appliance you have back to the negative terminal and the process repeated again. Are we together? Whereas for the electron flow, it's the opposite. You start here all the way around back into the same battery to the positive terminal. Again, this just emphasizes on the direction of your flow. Are we together? Please know the difference. Your conventional current flows from the positive to the negative. To be specific, from the positive around the circuit to the negative. Are you following? Very important to know those differences. Okay. And then I see IMS is at a place where the network is not so good. It's on and off. Right. This for me is most probably the most important slide. Okay. What I mean with most important here is that it shows the relationship between your three important concepts, especially if it has to deal with the flow of your charge. Are we following? Okay, so it shows the connection between your let me just quickly make Francis. It shows the connection between your current okay, my writing is only on the other side. It shows the connection between your current, your voltage, potential, and your resistance. So at first, we just want to explain some few things here. Please go through this. What is potential difference? What is the resistance? And how are they connected to one another? This triangle that we have here at the bottom shows you how you can calculate it, right? The way I remember is that V is king. Yeah? V also comes because without the voltage, there will be no movement. Without the power source, there will be no movement altogether. So V is king. You have your current multiplied by your resistance will then give you V. I'm sure we all know how this triangle works, right? And please get the units. The voltage here, then the current would be in amps, and the resistance would now be in ohms. Please understand that. Yeah? And they also differ depending on whether your connection is in series or whether your connection is in parallel. Yeah? That's the main thing on the circuits. Again, this just shows you a little bit of a relationship of your current and your potential difference. So the resistance versus the length here. So what happens here, there is a direct proportion as the resistance goes up. Or I mean, the resistance is also actually dependent on the length. So as the length go up, the resistance will also go up. The opposite will happen. As the length reduces, the resistance will also reduce. That is why you are having this linear relationship. Are you following? Okay. So in some cases, you can also have a non-linear relationship. Are you following, guys? Okay. The more voltage you have here, what will happen to this? Actually, this is a little bit, but not increasing direct or at a specific rate. So this is just showing you a little bit on that part. The other thing I wanted to look at was more on Ohm's law. Yeah? I want to just go to that part. This is, yeah. On Ohm's law actually relates your current, your resistance, and your voltage. Are we following? Now, the relationship between this, because if you take your current and you take your voltage over here, the relationship is directly proportional. Are we following? So as long as you have this situation, then you are obeying Ohm's law. Yeah? If it happens that it's not direct, then it doesn't obey the Ohm's law. It's good to understand this concept. Yeah? And then, as I said, guys, I'm quickly moving through this. The next part is to look into some series and parallel connections. Okay, so we understand how they work, isn't it? Some series and parallel connections. Series is the same line, so you could have something connected here and another one connected there. They are the same line. Whereas for a parallel connection, you would have it connected here, and then you would have a separation. So that's one pathway. You would have another pathway here. Okay, so the first pathway is up there, the second pathway is down here, but then they have to be connected together with one another, connected together, and then the source has to come from somewhere and going out somewhere. So what we mean with the parallel connection is when it comes here, you can have that path, the electrons can also go in that path. Maybe the appliance we're connecting there, we could make them bulbs. Are you following, guys? So this is just one pathway in the same line.
Please repeat on parallel.
Pardon, I can't hear.
Please repeat on parallel.
Parallel, what I'm trying to show you with the parallel part is that there are alternative pathways. So if the electron maybe comes over here, right? If it comes at that point, it can go up there and it can also go down there because the conductors can provide two alternative pathways. At the end of the day, they move through there, they can light the bulb up, and then they come and recombine or rejoin one another, and then they flow again, and the process repeats. Does it make sense? So
Yes, sir, thank you.
In a parallel way, you would have something like this, one way there and then another way there. Are we together? Which will eventually come together and continue the flow. Whereas for a parallel, I mean a series one, you only have one direction that it's flowing. Are you following, guys? Are you all following?
Yes,
Okay.
sir.
Yes, sir.
That's very important. Now remember, I said that your current, your voltage and your resistance will be affected by the way that your circuit is connected in series or is it connected in parallel. For example, the resistance is much more than the resistance in parallel. Are we following? Sometimes it keeps the same. So that's one thing that we want to emphasize. And I try to one another. I see that someone is moving too much over there. Nisuku, we want you to sit still, please. Thank you. Okay. So I try to put them next to each other so that we see what happens over here. All right. This is just to show you that in series connections, okay? In series connections, we said that everything is in the same line. Are we following, guys? Are we together? So if we look at this situation, we can say that here the ammeter is in series. Your resistors here is also in series with one another. Are you following that? So the focus here is to show you the electric appliances that we have. The resistance here or the resistors are in the same line. Whereas for the parallel, again, you can see there's one pathway over here, and then there's another pathway over there. Does that make sense? Two different pathways, okay? That is to show you the basic setup. Now, when it comes to current, what happens to current? And that is the one thing that I want to emphasize here. Let's take a different color so that maybe it can come out a little bit better. Now, when it comes to current, we want to see how will the current be affected by a series connection and how will it be affected by a parallel connection. Are you following me? Okay. Now, it's very important for us to read here. The current denoted by this, in this case, it's a capital letter I, not an L. All right. Now, what happens is that current in the series connection flows through each of the constants that we have, your electric appliances, for example. Are we following? So the same current here, the first current will be equal to the second current, it will be equal to this, the third current, if it's flowing through the same path. Are we following that? Is that making sense? Okay. Now, we know that current can be calculated from this situation here, where we said that V is king, current will be equal to voltage divided by resistance, isn't it? So here we said current is equal to the potential difference, which is resistance, divide that, voltage, sorry, divide that by the resistance. Are you following? So if you are given some questions like, okay, let's say, for example, you had this amount of potential difference, right? Let's say you had that voltage over here and the resistance here was maybe here in series, right? That you added together. If you want to get the current, you get the the difference between that or the ratio, and that will give you your current. Does that make sense? Okay. Now, current is then measured with a ammeter. The ammeter has to be connected in series, in the same line. Okay. And the symbol that we use for that on the electric circuit is that capital letter A in the circuit. Are we together? All right. Let's look at the parallel one. Now, the total current through a circuit. Let's quickly read together. The total current that you have through the circuit is the sum. What does it mean if you say the sum? You have to add them together, or you plus them, or you add them together. Are we together? Sum of the current through each branch. What do they mean with each branch? So let's say we come here, and then here we've got the difference here. Maybe we've got the, let me do this. Let's try to use colors to our advantage, okay? So let's say I've got this current coming in here, all right? Now that current can now go two ways. So the first one is, say, the red part up there. The second one, maybe we can make which color? Maybe the blue part down here, okay? The blue part, all right? And then eventually they will then recombine with one another. Sorry. And then let's try to get back to the green. So they combine together and then they exit as green. Now, what do they mean with the sum? Let's quickly look at that. So let's say you had a total of 3 amps coming in there as the current. Are you following? Now, what's going to happen here is that each branch that you have here, in this case, we've got 2 branches, right? The current splits between them, right? And the split of that is in the same amount. So basically, because you have this first branch and the second branch over here, you're going to divide the total current by 2. If you had 3 branches, you will divide the total current by 3 or 4 or respectively. Are we following that? So what's going to happen? This one will have a current of how much? 1.5. Now, sorry for my handwriting. This one would have a current of 1.5. Are you following? And then they say that they come and they recombine. What does that mean? They come back together, the 1.5 from here and the 1.5 from here adds, and it continues as 3 amps a year. Are you understanding? Therefore, if you maybe ask, maybe you had an electric appliance here, maybe the bulb in there and another bulb here. So if you are asked a question on this, you will then use this one for that. I will forget it because it has split. So your current value that you'll be using is the one that was split. Are you following? Whereas for series, we are saying they are the same throughout. So in a series connection, maybe in the first bulb, your second bulb, what's going to happen is you've got the 3 amps coming here. It's just the same. This guy will get the 3 amps. This guy will also get the 3 amps. Does it make sense? So that's why we would say that they are equal all over. So it's very important to understand what happens to the current in a parallel connection, what happens to the current in a series connection. If we master this, then the circuit calculations become a little bit easier. Does it make sense? Okay, are we all following us? Any questions from your side? Are we all fine? Okay. My online people, fine. You understand how the current works for your series or parallel connection?
Yes, sir.
Okay, that's good. All right, so let's then move on. Let's quickly clear this. Okay, we don't need to clear it. We can just go to the next page. Yes. Okay. Okay, thank you. So again, just as we have looked at the other side where we were looking at current, now let's look at potential difference. What's the other name for potential difference? This is voltage. Guys, I think this is the most important 2 or 3 slides that we're going to do here. The first slide was on current, the second slide is now on potential difference, and the other one will be on resistance. Because you will need to know the connection, how you do the calculation, okay? So we try to make it as vivid as possible so that you can also learn with this. So what's happening here? In a series connection or in a parallel connection, in connection or in regard to voltage. So let's read through this again. The total potential difference, because that's what they normally ask you. What's the total potential or the voltage in the circuit? okay, will be from the voltage, I put it there, from the power supply. So where does the voltage come from? So if you have a power supply like this, for example, right? And I say that this is just one battery, isn't it? And I tell you that this battery is maybe a 3-volt battery. So I tell you, use the same battery, but now this time around, you would then be using 2 of this. So the total here would be how much? Will be 6 volts. Are you following that? Okay. So this voltage that we're talking about is basically the energy that you need to move the electrons that are carrying the charge. Are you following that? Okay. Now we want to see if that battery is now connected in series or if it is connected in parallel. So we've got another battery system over here that is connected now in parallel because we've got 2 branches, and the A here is connected in series, 2 batteries. The B here is connected in parallel. Are you following? So that's what we want to establish here. Now what's going to happen here, that power that you are sharing between the 2 components according to their resistance. What it means here is that, let's say your voltage that you have here that's coming in is, say, for example, 0 point this. Are we together? What are we calculating here? How do you calculate voltage, by the way? From the triangle, we've got V is king, your I and your R, right? So the voltage here will now be the current multiplied by the resistance. Are you following that? So we've got the current here as your 0.36 multiplied by the resistance over there. We've got the same current multiplied by the resistance. So what we are trying to emphasize here in series is that if you have it together, let's say you've got that voltage that's coming in from the battery source, maybe we've got the battery source here, and it is then coming to flow through a resistor. Are you following? So if you do the calculation, is whatever voltage that you are having there, you will then multiply that with the resistance that you have from that one. Are you following? That's what we're trying to show you. Maybe you had a second resistor here that continues there. So remember, the current that's flowing in a series is the same. Are we together? So if the current here, maybe you do your calculation, voltage divided by resistance, you got the current to be 2 amps. These 2 amps are the one that will flow through that, and the same 2 amps will come and flow through the other resistor. If this is a resistor 1 and this is resistor 2, are you following? So it will, because they are connected in series. If it was in parallel, then that current will be split in 2 equal parts if it was 2 branches, right? If it was 3 branches. Are you following that? So when you are doing this calculation, because you get the product of your current and your resistance, if it's in series, it's straightforward. You can just simply multiply them. Are we together? But then, if it's in parallel, what happens here? Your potential difference in parallel for each branch is the same. What does that mean? So if you have this branch here and that branch, the potential difference that you will have will be the same. Are we following? In a parallel connection. Now in circuit B, I didn't put the circuits here. Remember, if you are going through this, I'm actually supposed to put the circuits on the same drawing. The circuits that we are referring to, if you're going to use these notes on your own, the circuits that we're referring to, where's my, let me just quickly go back. Sorry. The circuits that we're referring to are these 2 circuits. Yeah? Are you following, guys? So every time we are explaining the series or parallel connection with the current, the voltage, or your resistance, this is your circuit A and this is your circuit B. Whenever they are talking about these 2 circuits, it's with reference to this A and with reference to the B. Are you following that? So what they're trying to say is that when you're connecting, what happens here when you're flowing through that. So just bear that in mind. Eh? So if we read through this, potential difference, here where they talk about the circuit B, we refer to the other one. Actually, I'm supposed to, maybe in the next upgrade or what, we just put it there so we can view that as well. Yeah? So what happens is that the potential difference across each of the bulbs will be the same. Are we together? So if that voltage that was created from the circuit B, if we go back to this, the voltage that you have there from these 2 are 2 volts, then each of them will get the 2 volts. Are you following that? Okay, and remember this 9, I mean, the things that we're calculating here were based on this resistor 10 here and the resistance 15 there. So that's why we were calculating with the amps that we are having over there. So when you're using this on your own, please understand where that 10, 15, or this current is coming from those two circuits. Né? Okay, unfortunately, we do not have them on the same slide. So in the next upgrade, we will do that. So when we go through that, if an additional bulb were to be added in branch 2, are we together? All right? In series to bulb B, the potential difference that you have there, the 2 volts would be shared between the 2 bulbs with 1 each. So what we are trying to say in the series connection is, if you had to add an additional bulb over here, the current that was coming in here as 2 volts will be shared between these two as 1 volt each. Are you following that? Is that making sense? So if you go through that, just go and read through this. Mr. Simba will emphasize more as we're doing the questions. No? Okay, so that's what we have in your parallel setting. Then finally we get to the resistance. I'm sure most of you are familiar with the resistance, isn't it? So in series, the resistance is very easy. They always talk about the total. Remember, we were looking at the total current, the total voltage, the total resistance here. So that would be the sum of all the resistors that are there. In this case, we've got this 1, 2 over there. We add them together just as they are. The 10 plus that would then give us the 15 that we have over there. Is that making sense? Where this is a little bit different, okay? This is just to get the total. We just want to get the total resistance. And then if you want to get the total current here, what will happen here? The current, you need the voltage. Let me say the voltage in here was 12 volts, for example. I give it to you as 12. So if you are asked to calculate the total current here, go back to your triangle there. You'll see that current will be voltage divided by resistance, isn't it? So if they ask for the total, you take the total voltage and the total resistance as well. Are we together? So you would take that total 12, you would then come and divide it by that total 15 ohms, and that will then give you the current there in whatever amps that we're looking for. Is that making sense? And that is how these questions are normally structured. They ask you for the total. Is that making sense? Okay, any questions? Are we fine? Okay, good. The next part now is how is resistance in your parallel setting? Now, this is what we use almost in every household because the resistance is reducing because you've got the fraction there. Yeah? So in the total resistance in a parallel setting would now be the sum of this. I almost said the inverses, but 1 over that resistance, 1 over that resistance. So if resistance 1 was 10, and the other resistance was 5 ohms, you would put it always 1 over whatever resistance that you are having. Are we together? So the moment you make it 1 over, do you see how that changed? From 10, it becomes 0.1. From your 5, it becomes 0. Are we together? So we add that together, then we get this part here. But at this stage, you are not done yet. We want the total resistance. We do not want the 1 over that. Does that make sense? Are we together? So in other words, now you need to make the total resistance the subject of the formula, right? If you do that properly, you will see the resistance will now be 3.3, which is much less than these two things added together. You remember in series, when you added them together, they had a total of 15 ohms. Now they are having a total of 3.3 ohms, but it's the same resistance that they're using. Are we together? The fact that we introduce the fractions, it reduces significantly. And if you had to add another resistor over here, it will even reduce more. The more you add, the more it reduces. So all these bulbs that you have in your household are connected in parallel. Are you following that? Because we want the resistance to be low. Why do we want the resistance to be low? What is resistance? It is opposing the flow of your electrons, isn't it? It doesn't want the electrons to flow. So that opposing flow, that opposition, it's actually anti-current. If it's more, that means you have to push more in, more energy, and that's what we want to avoid, right? Okay, so this is the situation for your series connection and then also your parallel connection when it comes to your three main important components in electricity. Guys, if we understand these three slides, we are done with circuits. Has that made sense? Okay, are we having any questions, my online people? Let's see. Any questions? Nothing on the chat box? Yes.
So when is it that when you calculate the resistance in a parallel circuit, the answer has to be in the reciprocal?
It's the same thing. It's exactly what we shown here. What it means there, Luis, with the reciprocal engaged. Let me just quickly clear my board. You see what happens here. Look at this part. After you have put everything over one, right? You add them together. And when you put the 1 over 10 is 0.1. And then 1 over 5 is 0.2. So when you add these two things together, you get 0.3. Now, I don't know whether the highlighter will work. Maybe I just take a normal pen. What color do we have here? I think that's enough. Oh, that's fine. Now, Luis, I'm going to take from this point and come here. 1 over the total resistance is equal now to the 0.3. And at this stage, that's where you do your reciprocally. So in other words, you want to make your total resistance the subject of the formula. So a short version is just to say that you're going to put this thing 1 over that, right? But in maths, if you had to do it the mathematical way, the total resistance would now be 0.3 over 1. Are you following? And then because you've got one term over one term here, you could do your cross multiplication, right? So if you do your cross multiplication, or you could do, let's do that. 1 times 1 would be 1, will now be equal to 0.3 multiplied by the total resistance. Remember, you want only total resistance, okay? So we want to make that the subject of the formula. So we will then have to divide here by 0.3. You apply the same here. They cancel out, which means your total resistance would just be equal to this part over here, right? 1 over 0.3. So what happened here? That 0.3, you reciprocal, you changed it around. Does it make sense, Luis?
Yes, sir.
Okay, let's see what we have in the chat box. Can I ask questions on the group? Yes, you can ask. I just don't know how to pronounce his name. Let me ask your brother. How do you pronounce your sister's name? Risho. Rishiwa. Okay. Yes, Rishiwa, you can ask questions. Do you have a question? You can unmute yourself and you can ask a question. Do you mean on this chat box or you mean on the WhatsApp group?
WhatsApp group.
Okay, you mean during lessons or afterwards? Maybe
Afterwards.
Afterwards, yeah. Whenever we have time, yes, by all means. We might not just be able to get back to you immediately, but yes. And I always encourage that if you ask questions, maybe it's something you're working out, you can take a picture of that, send it to us. Either you send it on the group or you can even send it to us personally, okay? And say, no, sir, or ma'am, I'm getting stuck here. We are always willing to help. Is that okay?
Okay, sir.
Okay, guys, so we have covered the main part over here of that. And then we get now into the electric appliances at home. Yeah? This mainly deals with some sort of connections that we have to do. Where do we use them? Your kettles and all of that. First, we want to see the conversion of your energy from electric to kinetic or whatsoever. We look at all of that. What I want to put out there is that in these cases, mainly, we will then be calculating your energy that you are consuming. Sometimes if we have time, I normally give a project to learners to go and find out how much energy you're using in your household. Yeah? You can calculate it depending on how much the bulbs that you're having, especially if you have this prepaid electricity, right? When you buy them, they will tell you these are the kilowatts per hour that you use for the month. And then you go and check, oh, this thing is just 1.4. Oh, it's going to switch off very soon. And you go punch in that code and then it becomes, say, maybe 1 or 132 whatsoever. Yeah? How can you reduce that? If you go and buy a bulb that says it's a 90 watts, for example, what does it mean? it means it consumes 90 joules every second that it's on. Are we following? How do you convert the joules from there into the kilowatts per hour? You understand? So those are the type of calculations that we are doing. We need to understand first how to get the energy. The energy you can calculate in different forms, especially on the formula sheet I gave you. There are at least 3 or 4 different ones that you can use, and it depends on what you're given. So if you are given power with time, how much power is being consumed in that given time, you can calculate it by using that. If I give you voltage with the charge, you can also calculate it this way over here. So again, guys, this is just for you to get familiar with calculating the energy. Then you convert the energy now to the kilojoules and so on. Is that clear? Okay, I'm not going to go too much through this, but it just shows you here again an example. In 2 minutes and 30 seconds, you have this kilowatt. So this watt basically means is joules per second, right? We put it in joules per second because we want this seconds and seconds to come and cancel out so that you only have it in joules. Are you following that? So what's going to happen here is, and of course, as I always tell you, kilo means what? Kilo means 1,000, yeah? Are we following? So you convert that 2.2, that will become 2,200, right? You multiply that with 1,000, and then you take that 2.5 seconds, you multiply, 2.5 minutes rather, sorry. You multiply that with 60 because you want it in seconds, right? So what do you have here? Here you just have joules, and here what do you have here? Actually, this was kilowatt less, so this is joules per second. The kilo is gone, and this would just be in seconds. The seconds and seconds cancels, then you would have it in joules. If you convert that joules by dividing all of that by 1,000, these 3 zeros cancels with that, and that will now give you 330 kilojoules. Are you following? So how do you, that's the amount of energy that you'll be using at home. Is that making sense? Okay, so this is just to show you those examples. Again, Mr. Simba will elaborate a little bit more on that when we are dealing with the questions. Okay. Any questions from your side, my online people? Hands up if you have questions. Chat box. Here, do we have any questions? We are fine. Yes, Kenneth. In terms of the calculation that I was showing you. Okay, yeah, I was a little bit fast. I can quickly elaborate to you. What we have here is, let's just clear the space over here. Over here, okay. You see what they are asking me, this is actually a real life situation, right? They're telling you that the kettle power rating, it means how much power, if you look at the power over here, right? So the kettle power rating is 2.2 kilowatts. So it depends on, if you want a very strong kettle, you're going to get a 4.5, for example, right? It depends on what appliances you're buying. The generator, when you want a bigger power rating, what. I will follow it. So the kettle power rating is, 2.2 kilowatts. And it takes 2.5 minutes to boil the water inside it. Now we want you to calculate the energy transfer to the water. Where is that energy coming from? In the kettle, you've got your heating element down there, yeah? And then that gets power from the electricity into the socket. And then here, due to convection currents, the water gets hot. Now they want you to calculate that energy that was transferred from the electric source to that. You understand? So if we remember that, we've got 2.2 kilowatts, and then that is in 2.5 minutes. So maybe let me just try to get a whiteboard here so we have a little bit more space. Yeah? Let's see if we can remember the the units there. So the power rating of that kettle was 2.2 kilowatt. Now, this watt that you are having there is the same as how much energy was consumed in a given amount of time. It's joules per second. You understand? So what I'm trying to show you is that 1 watt is the same as 1 joule per second. Does that make sense? So that you understand that conversion, right? And then we said that it took 2 minutes, let's say 2 minutes and 30 seconds for that water to boil. So we are converting that 2 minutes. So 2 minutes is half of a minute, right? That's why we say 2.5 minutes. Are we together? So that 2.5 minutes, we try to convert that to seconds because in 1 minute, they are 60 seconds, right? That's why we are multiplying this with 60. Does it make sense? Okay, so when we multiply that with the seconds, that value that we are getting over there, and then on this side, how much will we get there, guys? 2 times that is going to give you 120, isn't it? So half of one, that would give you 150. So this would be 150 seconds. Are we following? The reason why I want seconds here is, remember we were asked to calculate the energy. Are we following? So the energy, if you remember that triangle says the energy will be the power multiplied by the time. Now remember, energy is always in joules, or you could have it in kilojoules as well. So the time, I put it in seconds, okay? And then the power rate here, I'm putting it in joules per second. Reason for that is that this and this will cancel out. If I multiply that I have energy only in joules. Does that make sense? So the energy that we are looking for here, that we have to calculate, must be the power multiplied by the time. Now the power that we have was 2,200 joules per second. Multiply that now by the time of 150 seconds. Does that make sense? Okay, maybe I can put the seconds there. Seconds and seconds cancels. The product of that, the answer will just be in joules. So that's the amount of energy that you'll consume. So maybe it's just the conversions that we have to understand. It's almost like weights. When you are calculating, you don't use halves. You use per second. I will follow because so that you can cancel them out. That is what we were trying to show there. Does that make sense? Okay, so if we go back to this, let's quickly go back to our slide. If we go back to this, it's the same thing. So we took that power, we convert that to joules per second, we multiplied the 2.5 minutes by 60 seconds. When we get all of that, we were getting 330,000 joules. So if you want to convert that to kilojoules, you just divide that by 1,000. Those 3 zeros cancels there, then you only have 330 kilojoules. Does it make sense? Okay, it's just again, it will be strengthened with the questions that we'll be doing. Yes. So we've got to check there. Thank you. Can you see what Sir was writing? Oh, sorry, Francis, I need to share that screen. Basically, what we were trying to show you there, Francis, let me just quickly stop sharing the screen and see if I could reshare that part, if it's possible. Okay. It will not be possible at this point in time because I don't have that specific device that can use the screen as a camera. Yeah? The camera can show. So Francis, I'll unfortunately not be able to do that now, but we can sort it out maybe during break. What we were trying to say is Kenneth was just asking. He wanted us to repeat what was happening here. So we were just elaborating a little bit on how we got that and how we do that or why that had to be done. And it's all just about the unit. Just to sort out the unit. Are we following that? Okay. So guys, we might run a little bit late on time. So let's quickly go through this. Again, the charge calculations, we know how to do that. Then here's another way to calculate power again. So you can see on your cheat sheet that they'll all be there. We show how you can calculate current and power. Actually, this shows you all the possible ones. Also know how you can connect your one-phase plugs there. Where does the brown wire go? Where does the blue wire go? The green and yellow wire, what does it mean? Are you following? So this is the live wire. This is the earth wire. And then this is the neutral wire. Are we following? And then what is the purpose of a fuse? So that if the current is too much, then the fuse will break so that you do not destroy the electric appliance. Are you following? So this is just some of the few things that you can go through. Then this is just showing, you know, what it looks like if you have a grid. You've got your power station there that brings it here into this transformer, step-up transformer. It's been transported basically by the cabling. You've got the step-down transformer that now gets into the different households. This is just to show you what happens, how we get electricity before we get to the parts on transformers. Yeah? I'll skip through this. These are some common symbols that we use under your electric circuits. Then we've got the magnetic forces. This is now when you get to the magnetism part. Yeah? So the first part just explain what magnets are. We know any magnet has got a south pole and a north pole. They have the positives and negatives. Are we following? You can have this horseshoe magnet or a bar magnet. It shows you the opposites can repel, the opposite attract, sorry. The like ones repel, the earth magnetic field. But that's just the basics, how the fields are forming. I want you to read through this. The difference between a permanent or an induced magnet, a temporary or a permanent magnet. And then what I want to focus on is mainly your magnetism. What does it mean when we're talking about electromagnetism? It means that we are looking at the following. We are looking at electricity together with magnets. Basically, you are exposing electricity in a magnetic field. To do what? To get specific appliances. I will follow it. So in this case, I remember Mr. Simba was still explaining this. Remember when we had the class on the screen, then you've got the inverted thingy on showing your right hand will show left on the screen there. So this you can go through the notes, but it just shows you that if you've got the current coming this direction, and you've got now your magnetic field around here, how you can use your right hand and left hand rule. Again, we can go through this. I remember Mr. Simba was showing a lot of this. Let me just quickly see if we have this. Yes. You remember the Fleming's right hand rule and the left hand rule and what. So this is just showing you which part of it refers to the flow, which is the field, which is the movement, which is the current. Okay. So under the magnetic field, what I wanted to emphasize here was something we call the solenoid. What is a solenoid? A solenoid is basically when we have this coiling effect, yeah, of your electric conductor. Are you following? Now, you need to have that, especially if you are creating a temporary magnet, because the flow of the electricity allows that steel to be magnetized. Are you following? So at scrap yards or speakers, and speakers are using permanent ones, there's applications around there. So again, if you can see the pictures, it can help you a little bit understand what a solenoid is and how it works. Yeah? Difference between the right hand grip and the left hand grip. We will go through that as we're going through the questions there. Okay, I just don't want to spend too much time on this. The motor effect, again, we put it for you in such a form that you can see the picture. So what happens here is you create an electric field from not an electric field, but a magnetic field, right? So the magnets are separated. And then you are passing a current, go back. You are passing a current through that field. Are we together? So what is going to happen when you are passing the current through that? Again, with your right hand, left hand rule, you'll see where the force is going. But I want to sort of like emphasize the following. Let me just go back to this part. This is what happens in an electric motor, right? You've got the magnet here. So the magnet is separated. So in this section here, you've got a magnetic field because of this magnet that you have over there. And then you have a current. You see, this will go there, and then the current has to complete. And again, you can also have the magnetic field there. So what happens is that this situation will cause this thing to move. You understand? The presence of the magnetic field and so on. So when that starts to move, you have a force moving down, and then you create this motor effect. Does it make sense? I don't know whether Elon Musk is using the same concept in his vehicles. Does he use the same concept, Mr. Summer? Yes. Okay, so there is some extent to the same concept. Are you following? So this is one part of looking at it. Again, the pictures are there to show you how it works. It just elaborates a little bit. Loudspeakers, we show you how loudspeakers are working. Some explanation. Sometimes they'll ask you that. Look at this. You've got a permanent magnet here. You've got a solenoid here. You see what's happening? Then it will cause the movement, the vibration that will create the amplified sound. So again, that will just explain a few things. An induced potential. So what does it mean if you induce? You're forcing this to happen. Are we together? It's not there naturally, or it's not spontaneous. So what's happening here is, again, you've got the magnet there, and then you've got this wire that is moving there. Are we together? What I mean with this is actually the solenoid that you are having here. You move the magnet back and forth in that solenoid. Does it make sense? So what happens here? On the other side, the magnet was stationary for the motor, right? And then the electricity was moving, and that created that movement. But what was creating there? The movement. So now here you are creating electricity, or you are creating, not electricity, but you are creating a charge without anything else but the magnet and then a conductor. Are we following? Most probably the copper. So what I want to show you here is, look at this. So you've got the solenoid here, this effect over here, okay? And that is now connected to, say, a voltmeter, for example, to show that there's electricity being generated. So if you take this magnet and you move it in and out here, back and forth, then you will create some charge. Does it make sense? Without any battery. So that is what they mean with the induced one. Does it make sense? This has been used a lot in, what do you call those devices on the bicycles? Dynamos, what do you call them? Dynamos, right? So dynamo, what happens is that it has got the magnet that should move, and then there's the solenoid around it, right? So the magnet is being moved by, if you push it against your wheel or your tire on your bike. So as you are pedaling, you are moving the magnet, right? So you get this back and forth movement in the solenoid, and it creates a charge. And that charge, or that is used now, the current is used to light the bulb up. So you don't need any battery in it, you just need movement. Are we following that? So this is what they mean with the induced voltage or the induced potential. Again, you can manipulate that by the number of coils you have, or the strength of the magnet, or you know, the all those different things, how much you are creating. So this is just explaining that. So we've got that concept, and then we also got alternators, very commonly used in cars. Are you following? So again, you've got the current thing. I mean, you've got this, not the current, but you've got this magnet over here. So on the alternator, the magnet can move as well, so that you can create your electricity. So that's one part. Yes, the dynamos. This is what I was talking about. So what happens here is that this part here will then be creating. The reason why they've got split rings is more for the engineering part of things, so that they are more durable and so on. Okay, so this is just to show you some of the examples that we have. I'm rushing a little bit. Microphones also use more or less of the same thing. And then finally, let me just look at transformers. How much time is it? Yes. The alternator. No, the alternator is the engine. As everybody know, the alternator, what the alternator is doing is that the battery is just used to start the car. So when you start the car and you're driving the car, your car is using some power from the battery, right? So for the lights, for the tape or the radio or whatever is being used in the car. So if you do not recharge that battery, it will deplete. So the alternator is recharging the battery. You understand? That's the function of an alternator. Are we following? So if the alternator is not working, I can just drive that car from here home and the battery is flat. So the moment the battery is there just to sort of like start the car. And then from there, the car runs on itself because the alternator recharges the battery. And that's why you need to change the water of the battery and what. And then of course, this thing will also deplete at some stage and you buy a new battery. At least you can use it for 2 years or so, rather than just maybe 10 kilos or so. Okay, last thing on transformers. The important thing here for transformers, we're gonna put it here in the middle, is that wherever the power source is coming from, you want to have it in such a way that you need to step down and then you have to step up. What it means there is that you want to step up so that you can push this thing for distance, kilometers and kilometers out together. Then power is here in Buntu, right? Mainly. But it is supplying power to so many different towns all around Namibia. Even in Kitmans or whatsoever, or they could have a substation somewhere, but it's not distances just like maybe 10 meters or 5 meters. It's kilometers that we're talking about. So to help boost that, and that boosted one comes, and then it is then sort of like, unboost, so that you can use it in the, at your home appliances. Otherwise, it will blow everything up. So how does a transformer work? Again, look at this, 400 kilovolts, that's a lot, guys, okay? So, and then compare that to the 230 that we use in our households, yeah? So, we've got two basic types of transformers, the step up, the step down. Now, for you to decide which is step up and step down are based on the coils that you are having and the voltage that's going through that, right? What do we mean with the coils? The number of turns that you have for the solenoid, if I could put it that way, yeah? So how many turns do you have on which side of it? So what happens here, you are using a magnet. So there's a magnet here, so there's something coming in and then something has to go out over there. So in that magnet that you are using over there, let's just make sure that we have accepted, okay, he's going. All right, so the magnet that you are using here, you've got these coils that are around here, right? Are we together? And then you've got some coils that are also on this side. So the number of coils or the voltage that's coming in there could be maybe the voltage from the primary source, the voltage that is going out to the secondary source, the number of turns that you are having at the primary source, and you understand. That is the basics of a transformer. So what happens is it looks like this. So here we're trying to show you the difference between a step up and a step down transformer, okay? So on a step up transformer, the input, in all of them, they're actually just alternating current. So when it comes in here, it is having much less turns compared to the part where it's going out. Are we together? So that means it is not stepping up, meaning from small to big step up. Are you following? Where is the other way around? From big to much less, you are stepping down. Now that step up and step down has to affect the voltage that's coming in here. Is that making sense? And that is what we want to analyze. What's going to happen here? But the basics, we need to understand that this side where it is coming in is referred to as the primary coil. Are we following? And then the side that it is going out is referred to as your secondary coil. What will happen here? The primary coil, it remains the same. Where it's coming in and where it's coming out is your secondary coil. Okay, so in a step-up transformer, we have fewer turns here at the primary coil as compared to that of the secondary coil. Are we together? This means that the induced voltage, what is the induced voltage? The voltage that you are causing. Are we together? The induced voltage across the secondary is greater than the applied voltage across the primary coil, increasing the potential difference. So these two statements here that are showing you is just to elaborate on what it looks like, and that is then being complemented by the different drawings that you are having today. Of course, we're not really going to ask you to draw it, but we will ask you to do the calculation. Are you following? How do we do the calculations? So you would have situations like this. Okay, so what I want to emphasize here is that the V is for the voltage. Are we together? Is that making sense? Okay, and then the N that we are having here is for the number of turns. Yeah? How many turns do you have there? The voltage that is coming in from the power source, the battery or whatsoever. Are we following? Okay, please understand that. The V and then, so here, just as that drawing was saying, is just to show you for a step up. I'm starting from small turns to much more turns. Are we together? So the number of turns for the secondary, are we together, are much more than the number of turns for the primary, because you've got less turns here at the primary, but more turns here at the secondary. That's what it says. Are we following? The same applies here for a step down from a lot to much less. The way I remember it is on the number of coils, whether it's a step up or step down, because I'm coming from less to more, step up, né? From more to less. I think maybe they even named it based on that, step up, step down, but it's up to you, whichever works for you. Are we together? Yes. Question? Fine. All right. So how do we do these calculations? what's going to happen is sometimes you will be given one part and then they ask you to get the next one. Are we together? So the ratio that we're talking about is that you're doing your divisions. Are we together? So again, the step up, step down, this tells you the voltage that will be there, the number of turns and so on. So we can compare this in terms of the voltage and in terms of the number of turns. So let me show you with a more specific example. Okay, unfortunately the answer is there already, but here you've got a transformer that has an input voltage of this amount. Are we together? And the output voltage is this amount. And then they go further and then they tell you the number of turns on the primary coil is 2000. How many turns will you have on the secondary? Are you following? So you can start. My advice to you is start with what they are asking. The secondary coil, what are they asking for? The number of turns on the secondary. That's what you start with, to avoid a lot of complication in your mathematical calculations. Yeah? And then we go further and then we can say, okay, we use that formula. Then we've got the number of turns on mine, because I've used the secondary here, then this will be the primary, right? That will now be equal now to, what I want to emphasize is since you use the secondary on top, that will now be the voltage of the secondary over the voltage of the primary. Are you following? And then we make this the subject of the formula, which means we'll just have to multiply with the primary here so that they can cancel out, and that is then multiplied by the primary. You plug it in. This is exactly what we have over there. The primary, your secondary is up there, divided by your voltage of primary, and then it will show you that you've got how many? 400 turns. Now, is this a step up or a step down transformer? Step down, because it started from 2000 turns to 400 turns. Does it make sense? Is that clear? Okay, so that's one way of looking at it. Another way I wanted to show you to calculate this also, it's not very common in some of your textbooks, but you can also use this if they give you current. You can use that relationship. Yeah? If they use the current. So an example of this would be something like this. Here you've got a transformer that has voltage of this, right? And the voltage of that. So this is now the input, and then this is now the output that you have over here. And then they tell you the amps that you have for the secondary one is that. Are we following? Then they ask you to calculate the amps here, calculate the output power, or I mean the input current. So you can use this relationship to do that because you've got everything else except that one. Are we following? So you go and substitute, you've got now your voltage from the input, right? Which is your input is always your what? Primary or secondary? Primary. The input is the primary, né? And the output is the secondary. Please make those notes. And then you come and plug it in. Once you plug this in, then you would come to the answer that current that you're looking for would be this. This is not very common in your textbooks, but we just put it there as an invention. Okay? I'm not sure whether I also include it on that part that we have over there. Okay, guys, so that means we have come to the end of the revision. We have tried to touch everything, maybe not in detail as we would wish to, but just to give you an idea. Okay, are we all together, guys?
Yes, sir.
Is that clear?
Yes, sir.
All right. For this reason, we said that we would like to do it over the 2 periods. Now, Tashia, you've got a question.
Yes, sir. I'd like to ask or know whether sir is gonna put this recording on the group, like the
Yeah,
live.
I'll put the link. It's easier for the link, and since most of you do not use Facebook, I opt to just put it on YouTube. Sometimes you just
Okay.
make it private, so not all the other people are seeing. But now I make it public because there's also a marketing technique for us. But if I put the link and you click on it, then it will just go to a YouTube video and you can have a look at it.
Okay, thank you, sir.
Okay, and the notes, the problem with this is, I think this one was about 60 megabytes. If we convert it to a PDF, maybe it would be less. Then I can also share this as a PDF on the group there, so that you can have access to this as well. Okay, any other questions? If there are no questions, then I'm really within time. I was really aiming to finish before 11, and it's almost 11 now. Then 2 minutes to 11. All right, so you have an hour off. If you don't want the hour off, we can just jump into the question. Okay? What is there? Someone asked me. Okay. Shall we jump into the question? So is it too much? Too much information there? Okay, of course. The guys here have the questions in front of them. They can always do them. But we can quickly take an hour break from 11 to 12. Please, my people here, face to face, let's please come back at 12. Eh? Let us not go in bed sheet. I'll create another link and then I'll share that on that. Oh, no, let's just use the same link. I'll edit the timing on the link. So at 12 o'clock, you can connect to the same link. Okay.
Yes, sir.
Okay, have a best break, enjoy your break, and then we see each other 12 o'clock again. Yeah? Okay. Bye. Okay, no, we said we want to see you. Let us see you. No. I don't have the device, so you will not be able to see us. I don't have that device to connect the camera there. But it's fine, we can do it another time. Some people are happy. Okay, bye.
Bye.